My name is Jason Schuster. I'm a doctor of physical therapy. I own Intricate Art Spine and Body Solutions. It's a continuing education company teaching other doctors how to do a couple things. Before that, I was a fly fishing guide in between Patagonia, Chile, and southwestern Alaska for a decade. This is a clip from my muscle, mitochondria, and metabolic energy course. This is a great course, you guys. It's up and coming. I'm just finishing the course right now. It'll be up on my website in the next week or so. Keep an eye out for it. It's going to be a 5 CEU course all about how muscles work, how mitochondria works, metabolic energy, ATP, stuff like that. It's going to be a great course. Check it out on our website, intricateartseminars.com. Thanks, guys. Even after accounting for tendon, myosin, so thick filament, myosin, thin filament, active and passive tighten elasticity, only 34% of the absorbed energy could be explained. The extra tension that remains after stretch is due to tighten. Most of the absorbed energy during stretch is stored in non-crossbred structures, mainly in the springy tighten protein. So remember, they call it the spring protein. If you think about a spring, if you compress the spring, that is the initial energy that's put into the mechanism. You don't require any more energy to create more work. So you put the energy in, the energy is stored, and then the energy can be released in the tighten protein, which is springy, right? So if you compress a spring and it's hold compress, and then it undoes, that force all of a sudden comes out, and it appears to be coming from seemingly nowhere if you didn't see exactly how that spring or how the tighten protein was compressed in the first place. Really neat stuff. Prior to the discovery of tighten in the late 1970s, researchers sought to explain the extra eccentric force with cross-bridge theory. Again, we've talked about that. We just talked about that. That is not true. Studies have demonstrated that there's a role for tighten in the residual force enhancement after stretch, which is what we just talked about. So if you're stretching the muscle and then you stop, even for a time period after that, you can still produce more force than if you just had done isometric force. So eccentric into isometric allows you to produce more isometric force than if you just did isometrics. And that, again, as far as we can see right now, is from the tighten protein. And remember that increased isometric force after right following an eccentric contraction is called what researchers in the literature terms passive force enhancement. So we know more or less, like for sure, you guys, and this is why it's insane why this is not taught in school. We're as sure that tighten is doing this as we are that actin and myosin are doing the things that they're doing. So it's crazy that this is not taught in school. So tighten structure and function. So since the discovery of tighten, it's been speculated to contribute to passive muscle tension as well as sarcomere integrity. In 1986, it was demonstrated that tighten filaments transmit cross-bridge forces to the Z-disc. Used radiation to break thin filaments and electron microscopy to show that damage to the tighten protein results in a reduction of active tension in single fibers as well as axial misalignment of thick filaments or the myosin filaments. Without the tighten filaments, force generation by the cross bridges is highly inefficient because energy from cross bridge interactions is lost to thick filament displacement at the expense of longitudinal tension. So if you study like single sarcomeres or fibers of muscles, you guys, and you take the tighten protein out, you lose the things like the residual force enhancement, you lose the extra eccentric contractile force. So when you remove tighten, the extra force and stuff that's incorporated into eccentric contraction disappears. When you add tighten back in, it's there. So everything that we can see about this indicates that this is actually what's going on, you guys. It's really, really neat stuff. Two linked spring elements make up tighten's elastic I-band region, and here's a picture, you guys. This is not super important stuff to know, but it's good to have a good general background of what's going on. And this is a good kind of review of some of the stuff that you guys learned in grad school. If you haven't taken this stuff yet, here's a good review. So number one in here, you guys, the tandem immunoglobulin. You can see on the left in the picture, tandem IG. Number two, we have the PEVK segment, right? So that's labeled right there, the little green stuff. Passive stretch straightens the folded tandem IG domains at relatively short sarcomere lengths with minimal increases in tension. However, to stretch the sarcomere length beyond the normal physiologic range causes the PEVK segment to be stretched, resulting in a sharp increase in tension. So we're using mechanics to increase forces, you guys, like passively increase forces. If you have a structure, like a material that has a certain elasticity, as you start to stretch something that's elastic, as it gets stretched more and more and more, it starts producing more and more and more resistance because it's getting tighter. So if you have like a rubber band that's like a circle here, and you grab both ends and you start to stretch it, the more you stretch it, the harder and harder you have to pull to keep stretching it more. That's more or less what's going on with the titin protein. It's like a little rubber band that's attached to your actin and your myosin filaments. Because these compliant and stiff segments are in series, titin-based passive tension is relatively small in comparison to active muscle tension. Thus, the conventional wisdom has not surprisingly been that titin, while elastic, is far too compliant to contribute to active muscle stiffness, which is wrong, you guys. This is a huge mistake in medicine. So many people that are in science believe that they really know like most of the stuff there is to know. So if they see stuff that doesn't immediately make sense to them or that they can't make sense of, they just say that it's wrong or that it doesn't exist or whatever. We see that happening all the time nowadays in mainstream medicine, which is one of the reasons why public health is worse than it's ever been, as our technology and medical understanding is better than it's ever been. And that's just going to keep getting worse, you guys. So that's why it's important to understand this stuff for medical practitioners in particular, so you can go out, get out of the health insurance field, start cash pay practices, actually treat your patients well, and actually help people, you guys. So this is all stuff that's important to understand if you're going to be able to maximally help your patients. The winding filament hypothesis. So this is way better than the sliding filament theory. The winding filament theory or the winding filament hypothesis, way, way better, you guys. So I was in grad school in 2012. Why weren't we taught about this? Just because it wasn't in the standard curriculum, and grad school teachers are petrified of like teaching new things that are actually true that aren't in the curriculum because they get in trouble for doing stuff like that, you guys. So the winding filament hypothesis, proposed in 2012, presents a plausible molecular mechanism for titin's role within active skeletal muscle sarcomeres in conjunction with both calcium influx as well as cross-bridge cycling. The winding filament hypothesis proposes that following calcium influx, so remember, acetylcholine goes from presynaptic cleft to postsynaptic cleft. That starts the sodium potassium pump. Inside the cell, calcium gets released from the sarcoplasmic reticulum, and that binds to troponin C. That's the thing that moves tropomyosin out of the way. That allows the actin and myosin to start contracting. The winding filament hypothesis proposes that following calcium influx, the N2A region of titin binds to actin, and because cross bridges not only translate but also rotate the thin filaments, the actin filaments, the PEVK segment of titin winds on the actin filaments during passive force or during force development. So when actin and myosin overlap, you guys, they don't overlap in a straight manner like my fingers. As actin and myosin are unlapping or overlapping, if you think about these two fingers, if this is actin, this is myosin, if they're overlapping like this, they're not just going straight, you guys, they're overlapping and they're kind of twisting around each other like that. So the titin protein is already attached to the actin and the myosin. So as the actin and the myosin are overlapping or unlapping, they're winding around each other or unwinding around each other. The titin protein is also doing that, and that's providing some type of extra friction. I think of the titin protein as like a zip tie, you guys. If you guys have ever done falconry, so I am a falconer. I had my falconry license, you guys, a long time ago, or not that long ago, but I've had a red-tailed hawk. Birds of prey, accipiters, buteos, falcons, stuff like that, they have hinged ligaments and tendons in their toes, you guys, so you can hear it. When they close their feet on something, you can hear it go click, 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 and it goes all the way down, and then it's passively locked. So when a hawk's foot grabs onto something and it locks into place, they no longer have to use muscle force to keep it locked, you guys. That's kind of what's going on with the titin protein, is it's providing like this passive force. It's really cool. So relatively little thin filament rotation is required to account for the observed muscle forces during eccentric contraction. PEVK binding to actin is hypothesis to resist unwinding. So the winding filament hypothesis. A, upon calcium influx, the N2A segment, the titin segment, which is the N2A segment, binds to the thin filaments or the actin filaments. So the titin that's labeled there, you guys, binds to the blue or the actin filaments. B, so the cross bridges wind tighten on the actin filaments in active muscles, right? So that in muscles that are active, when the actin and myosin are overlapping and unlapping, they do actually rotate a little bit around themselves, which adds the rotation of the titin, which adds the ability of the springy titin protein to produce extra eccentric force. Titin-actin interactions. The consequence of titin binding to actin during active muscle activation sufficiently accounts for the observed increase in titin-based stiffness upon activation in skeletal muscle myofibrils. The N2A region of titin is ideally located, separating the compliant tandem IG domains from the stiff PEVK region. So you guys can go back and look at that one picture a couple of slides ago with the PEVK and the N2A region and reference this slide here with that, and there's information on that slide as well. So this results in the modulation of titin stiffness via calcium-dependent binding to thin filaments, the actin filaments. When titin binds to actin in the N2A region, the low force straightening of proximal tandem IG domains in the I band seen during the passive stretch of myofibrils at slack length is eliminated. As a consequence, when calcium-activated sarcomeres are stretched, only the stiff PEVK segment of titin will elongate, resulting in much higher forces. So remember, the titin protein is springy. When you stretch a spring, it adds extra force. That's more or less what titin is doing. While several studies have proposed that titin stiffness increases in response to calcium, fewer studies have considered that in the presence of calcium, titin interacts with actin. So I don't know like really what that comment is doing. This is from this paper, you guys. Calcium is necessary for muscle contraction. So I don't know how important it is to see like maybe it is important. Can titin function independent of calcium? Maybe that may be interesting. Can titin do things to hold muscles together or to contract muscles in eccentric contraction without the presence of calcium? Who knows? Maybe it can. So immunoantibody labeling of titin in rabbit psoas myofibrils demonstrates that titin movement differs significantly between passively and actively stretched myofibrils, suggesting that titin interacts with actin filaments in active skeletal muscle rather than in passive skeletal muscle. Titin-myosin interactions. So titin interacts with actin and titin interacts with myosin. Experiments in 1982 reinforced the necessity of including interactions between the cross bridges and elastic elements in explaining the mechanism of residual force enhancement. So remember, the residual force enhancement, that's when you're doing an eccentric contraction, you stop in an isometric contraction, and then when you measure the force being able to be produced in that isometric contraction, there's extra force being produced that technically shouldn't be there compared to if you had just started in an isometric contraction and not gone eccentric to isometric. So starting in an isometric contraction produces less isometric force than if you go from eccentric to isometric. And even once you hold the isometric, the residual force enhancement lasts for a period of time after the eccentric contraction is done and you're in the isometric contraction. So super duper interesting, you guys. So in this study, they were looking at active muscle fibers from frog tibialis anterior, which were shortened prior to stretch. Shortening an active muscle fiber prior to stretch should reduce or eliminate the extra force if the residual force enhancement were attributed to the activation of an elastic element. So let's think about that for a second. Shortening an active muscle fiber prior to stretch should reduce or eliminate the extra force in the residual force enhancement which were attributed to the activation of an elastic element, which would be titin, right? So if you shorten the muscle overly before you go into lengthening, what these guys in this paper are thinking about is that should, theoretically, you should see a reduction in the residual force enhancement. However, when they did this, they reported the persistence of the residual force enhancement despite the pre-shortening of the muscle. So it doesn't matter if you like super shorten a muscle, then you do eccentric to isometric, or if you just start in like neutral and then do eccentric to isometric. That has no effect on the outcome of muscle force production. So they concluded that an elastic element developing within the muscle during activation is not slackened during shortening. So the tightened protein maintains its tension somehow during shortening. So the tighten is really only, it's seemingly like activated during lengthening. You can shorten the muscle all you want. The tighten still maintains its like stored elastic springy energy. Based on what we can see in electron microscopy, it seems that the actin that the tighten filament is mainly interacting with actin. It attaches to the actin and myosin via different structures, but it appears that the tighten is primarily interacting with actin rather than with myosin. So the concept that the actin filaments, the thin filaments, are rotated by cross bridges and thereby winding tighten upon actin is one of the plausible means of tighten myosin interaction, although additional mechanisms have been proposed. So because actin overlaps with myosin, if the tighten protein is primarily interacting with actin, when the actin overlaps with the myosin, then the tighten is also going to be interacting with the myosin. So now it's interacting with actin and myosin. Does that make sense, you guys? Binding of tighten on the thin filaments qualitatively resolves a mechanism linking cross-bridge force to tighten force. The winding of tighten on the thin filament on actin qualitatively resolves a mechanism linking cross-bridge force to tighten force. So this makes it make sense, at least, how the cross bridges are interacting with tighten. This unique feature of the winding filament hypothesis or winding filament theory is absent in other mechanisms that have been proposed. Per this study. Predictions of the winding filament hypothesis. The unmodified sliding filament theory fails to explain residual force enhancement. So the cross-bridge theory cannot account for the residual force enhancement. And I've got some numbers in here in a second, you guys. If I remember correctly without looking at the actual slide, I think the cross-bridge theory only accounts for like 12 or 13% of the total force that we can see being produced in eccentric contraction. So like 83% of what's going on is not accounted for by the cross-bridge theory. The winding filament hypothesis explains the observed force enhancement at low energy costs seen in eccentric contractions. During a lengthening contraction, the work done on a muscle by stretching it will extend, tighten, and in this process, elastic recoil energy is stored without the expenditure of ATP. So this is super important. Remember, you guys, I think this is the easiest way to think about it. Think about a big old spring, like a spring the size of my hand. When you're shortening your muscle, when actin and myosin are overlapping and concentrically shortening, think about that spring getting compressed. And then it stays compressed. That is stored energy. So the concentric contraction was doing some work to store energy and tighten. And then when you eccentrically contract your muscle or lengthen it, that stored energy and tighten can now be used passively, more or less, to produce extra force without producing like extra heat energy or anything like that. Very, very interesting. And this may also explain why you get that residual force enhancement that increases in a non-linear manner, you guys. So remember, the faster you do eccentric contraction, the more length in the muscle is, the more force you can produce. And then there's a bigger residual force enhancement afterwards. Tighten seems to be the best answer, the most obvious answer that we have for that right now. This is a clip from my muscle, mitochondria, and metabolic energy course. This is a great course, you guys. It's up and coming. I'm just finishing the course right now. It'll be up on my website in the next week or so. Keep an eye out for it. It's going to be a 5 CEU course all about how muscles work, how mitochondria works, metabolic energy, ATP, stuff like that. It's going to be a great course. Check it out on our website, intricateartseminars.com. Thanks, guys.